Suppose we have a coffee cup here with coffee inside it at some temperature T coffee. And on the outside of the cup we've got a sensor which is at TS and air around it which is at ambient temperature TA. Now depending on the configuration of the cup and how well insulated the mounting is for the sensor temperature will be somewhere in between the coffee temperature and the ambient temperature when things reach steady state. If we want a good measurement of the coffee temperature, a good estimate, then we'd like this to be as close to the coffee temperature as possible. So we'd like the difference between TC and TS to be small compared to the difference between TC and TA. We've got uncertainty in our temperature measurements. In this case, let's say it's plus or minus 2 degrees Celsius, typical of some of our transducers. We can indicate how well we're succeeding in making this measurement with what I've defined as a coffee index. And that's the difference in temperature between the sensor temperature and ambient, TS minus TA, divided by the difference between the coffee temperature and T ambient, T coffee minus TA. So if the sensor temperature is at ambient temperature, this index will be 0. If the sensor temperature is at the coffee temperature, this index will be 1. And it'll represent the percentage, how close we've managed to get the temperature sensor to the coffee temperature and away from the ambient temperature. So if we look at this calculation, let's suppose our coffee temperature is 80 degrees Celsius. And our ambient temperature is 20 degrees Celsius. So this is a hot cup of coffee that we've just poured. And we measure the sensor temperature, and we get that the sensor temperature is 70 degrees Celsius. So if we plug all of that in here, that coffee index calculation gives us 0.833, or 83%. That means that the sensor temperature is 83% of the way from the ambient temperature to the coffee temperature. So 70 degrees Celsius, although it's not 80, is still much closer to 80 than it is to 20. So it gives us an indication of what the coffee temperature is likely to be. Now we'd like to know what's our uncertainty in this coffee index that we're using for a measurement. It's got to be some uncertainty value, and we need to figure out what it is. Well, studying from our textbook tells us that the uncertainty in the coffee index depends on the uncertainty in each of the 3 temperature measurements, and then the degree to which the coffee index depends on each of those temperature measurements. So if I see a small change in the sensor temperature, then I'm interested in how much the coffee index changes with respect to a change in the sensor temperature, dCi dTs. And if I multiply that by the uncertainty that I have in my sensor temperature, then that's how big a change I'll see for that uncertainty change in TS, because this is going to be the change in the coffee index due to that change from uncertainty in TS. Likewise, I'll have a term related to how the coffee index changes if I change the ambient temperature, dCi dTA. And I'll need to multiply that by the uncertainty in the ambient temperature. Also, if I change the coffee temperature, my calculated CI will change a little bit with a little change in the coffee temperature. And these are all determined from the calculation from the formula which relates CI to TS, TA, and TC. So this one, if I have an uncertainty in my coffee temperature measurement, then I'll get an uncertainty in the CI overall. Now, because these uncertainties may be independent, then they won't all be acting all in the same direction all at the same time, at least we hope. So when we add these up, we square them and then take the square root for the overall uncertainty. And that's the formula that we developed for Gaussian normal distributed random variables in the textbook. So this gives us a way to estimate the combined effect of these three uncertainties on the uncertainty of the coffee index measurement that we've made based on three different temperatures. Now, taking these derivatives from that formulation should be pretty simple. So dci dt sub s, well, t sub s appears only once. It's positive. Everything else, if we just take the derivative of ts with respect to ts is 1, and we wind up with that equal to negative 1 over tc minus ta. That's a fairly simple derivative to take. The one with respect to ambient temperature appears twice, and I needed to take a little time to do my calculus, but once I went back to my first year calculus, this is what I got. Negative 1 over Tc minus Ta, that came from this negative Ta up here, plus Ts minus Ta, those terms there, divided by Tc minus Ta squared, and that came from this Ta down here. And finally, dci dTc will just be equal to Ts minus Ta divided by Tc minus Ta squared. So that's coming from the Tc down here, down below. So I've got those derivatives. If I knew what Ts, Tc, and Ta were, I could calculate all of those. If I knew what the uncertainty in the temperatures each was, and in this case I'm saying it's plus or minus 2 degrees Celsius, I could calculate all of those, and I could plug them in. And if I calculated these out, what I would get for dci dTs is 0.0167, dci dTA negative 0.00278, and dci dTc I would get negative 0.0139. Multiply each of those by 2 for 2 degrees Celsius in here, square them, add them up, and take the square root, and I wind up with an uncertainty in Ci equal to 0.044, or 4.4%. So the Ci that I measured is equal to 83.3% plus minus 4.4%. So these derivatives were fairly easy if you remembered first year calculus. But if we had a more complicated relationship for whatever we were looking at here, we would find that it may be more difficult to calculate those derivatives analytically. However, we could approximate those derivatives. dci dTs is approximately equal to the Ci value that we get if we put in Ts plus some small delta T along with T ambient and T coffee minus whatever Ci we would calculate if we put in just TS, TA, and TC, all divided by that delta t. That gives us a good approximation for that derivative. And if we do that calculation with delta t equal to 0.1 degrees Celsius, then all of the numbers that we get out from our calculation wind up being the same as what we got from doing the calculus analytically. If you can do this calculus, then by all means do the calculus. If you're having difficulty getting the derivatives, this estimate for the derivative, this finite difference estimate, will still give you a good answer for your uncertainty.